This is Geometry, Unit 4.7. Today we're going to be talking about the fifth way we prove triangles congruent, and that's going to be RHL, right triangle, hypotenuse leg. In the past, we've talked about angle, side, angle, side, angle, side, 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 and we've also talked about angle, angle, side. Those are the 5 ways that we have to prove triangles congruent. Before we get all the way into RHL, we're going to talk about a perpendicular bisector. We can do it with a compass, but we can also do it by folding our paper. So if you pick your paper up and carefully take point A and point B, alright, if you take point A, if it's easier if you just take one page at a time, take point A and point B and try to line those right up to each other. The more accurate you are, the better this is going to work out. And then make a small little crease. It doesn't even have to go down the whole page. Just crease the page so it shows right where you're at. Trying to put point A and point B right on top of each other and crease your paper. If you trace out that crease, you then have what's considered to be a perpendicular bisector. The more accurate you were with getting your dots on each other, the more accurate your perpendicular bisector will be. So, you have created right angles, and we know that our distance on each side is going to be the same. So we often put a tick mark there. Now, what's also kind of neat about this perpendicular bisector is any point that is on the perpendicular bisector. We'll call this point C. Any point on it, let's see what happens when we measure this. Let's see if I've done my perpendicular bisector well enough. So if we look at the millimeters, we have 10, 20, 25, 26, 27, that looks like. So CA is 27 millimeters. Coming this way, trying to line it up, be consistent. There's 10, there's 20, there's 25, 26, 27. That might be almost like 27 and a half. But it's just how we line up our ruler and where do we put our thickness of our line. Anyway, they're just about the same length. They should be exactly the same length. So they're both the same millimeters. So what do we conclude? Any point on the perpendicular bisector is equidistant to the endpoints. I know that's a lot of words there. Any point on the perpendicular bisector is equidistant to the endpoints. So we found point C to be equidistant to the endpoints. So we can put our tick marks on there. We're going to try it one more time. We're going to find another point. And we can take our ruler, we can try to measure this one. Trying to be as accurate as I can with getting the 0 part of my ruler right on the dot and the line. That's 10, 20, 30, about 31, 31 and a half. And if we measure over to this side, trying to measure from the same location, this looks like 10, 20, 30, 31. Maybe this is closer to 32, but it should be the same exact distance so that these are the same. They were both just about 32 millimeters. So what can we conclude? The same distance. Rather than writing all those words again, they are the same distance to the endpoints if you're on the perpendicular bisector. Any point on there. So this is what we've been talking about. It's called the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, let's take a look at what that means. We have a segment AB, and point C is on this vertical line that is the bisector of AB, and it is perpendicular. So it's considered a perpendicular bisector of AB. Then it is equidistant. That's not spelled equal distant, it is equidistant from the endpoints of a segment. If a point is on the perpendicular bisector, then that point is equidistant to the endpoints. So that makes CA the same length as CB. So we would put tick marks on those two segments. Our theorem points out that if we have a hypotenuse, which is the side that is across from the right angle, there's our hypotenuse, and a leg, this would be our leg. We actually have two legs of every right triangle. The perpendicular sides are always considered legs. The side across from the 90 degrees is considered the hypotenuse. So we have a leg in both triangles the same. We have the hypotenuse the same. And these are of a right triangle. Well, you don't have a hypotenuse without it being a right triangle. If we have that, then we're guaranteed to have triangles that are congruent. Then the triangles are congruent. If you have R, which is the right triangle, hypotenuse, and a leg in both triangles, then the triangles are congruent. We call this RHL. A lot of times they put a little hyphen in between the R and the H, but not required. RHL. Your book probably just calls it HL. We call it RHL so that it has three letters like all the other ways that we prove triangles congruent. Other ways were side, 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 angle, side, angle, side, angle, and angle, angle, side. Those are the other four ways. Then we have RHL. Now let's take a look real close at RHL. RHL looks like side, side, angle. And a way to remember that maybe is if you go backwards and say ASS, angle, side, side, you might know what that spells out. And that is not one of the ways we prove triangles congruent. The reason why we don't use side-side angle to prove triangles congruent is because if it wasn't a right angle, there's a great chance that would not prove triangles congruent. It would not be consistently accurate. But every time it's a right triangle, this pattern works. So that's why we change it up to become right triangle, hypotenuse, leg. So we're not going to call this angle side side. We'll only call it RHL because it only works for angles that are right angles. And this R stands for right triangle, hypotenuse, leg. Let's try this in a proof. So here we have perpendicular. YW is perpendicular to XZ. So this wording here, this symbol, stands for perpendicular. Perpendicular means that we have right angles. If we have perpendicular sides, then we have a right angle. And if we have a right angle, then we have a right triangle. There's a few changes in our proof. There's some notation in our proof that's not accurate. We're going to have to change that. But if we have a right angle, then we have a right triangle. So let's take a look at what we know. We know that from the given information, we have XY, which is across from the 90. So this is the hypotenuse. Those are going to be the same. We have the right angle, which we could either call those congruent to each other, like we do in several cases, or we can say that we have a right triangle. In this case, we're going to need to call it a right triangle because that's what the R stands for in RHL. The side in between the two triangles, those are going to be congruent, and that's going to be the leg. So you have the legs congruent, you have the hypotenuse congruent, and you have a right triangle. So you have RHL. So the triangles are congruent for RHL. So that's our plan. That's how we're going to go about this proof. So here we talk about perpendicular, because that's our given. We talk about the hypotenuse being congruent. That is there because of the given. So from this, we have gotten that the H, that's the part that we know for sure so far. In RHL, we have shown that the H is congruent. If perpendicular, every time you talk about perpendicular, this will be your next line. It's a great pattern that you will always see. Perpendicular, then right angles. So angle X WY, comma, angle ZWY are right angles. And that's because we had the perpendicular sides. If comes earlier, then comes now. It says then right angles, so we need to talk about right angles. Now, we could talk about how those angles were congruent, but that's really not necessary in this proof. So I'm not even going to have us discuss this one. That really shouldn't be there. So we don't even need that line. We're not going to talk about how the triangles here are congruent. We're going to talk about that down here. I'm not quite sure why this is labeled in this fashion. That's the problem with having them halfway filled in. Sometimes it's not filled in right. This should be a comma. So this triangle and this triangle are right triangles. How do we know they're right triangles? So the way we know that this is a right triangle is because of the right angle. So if triangle has right angle, we know we have a right angle and it's in the triangle, then right triangle. If right angle, that's what we talked about earlier, then it's a right triangle. So we're stating that these are right triangles. That's the R of RHL. What's the reflexive side? WY is being shared between both figures. And if you notice, from the right angle up to the point and the right angle up to the point, they're going in the same direction. So we're not going to switch the letters. So we'll say WY is congruent to WY. And that's the reflexive POC. So we did not prove these triangles congruent by side, 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 or side, angle, side. We definitely did not prove them congruent by angle, side, side. We proved them congruent by RHL. And if you like to put a hyphen in between the R and the H, you're welcome to. And that's tomorrow, so we are all set.